welcome everyone. Summer 2025, a new year, a new summer of seminar series. Tons of great speakers lined up. Very happy to introduce our first speaker of the summer, Ling Ren, professor at University of Illinois, a well-known leading researcher in consensus, both traditional and blockchain consensus. And today he'll talk to us about a new fine-grained model of sort of network communication, granular synchrony. So Ling.
Hey, thanks for the introduction, Tim, and for the invitation to spend the summer here. I visited A16Z crypto research team 2 or 3 years ago. Today, I'm happy to tell you a bit about granular synchrony. This is a new timing model for distributed computing for blockchains, especially for large-scale blockchains. I'd like to start with motivation, right? Why I believe we should study new timing models, since there are a few fairly established ones in the literature for decades. And then I'll tell you about what the model is and how we can solve consensus in the new model, and close with some discussions and future directions. So timing model. This is one of the most important aspects of formal modeling in distributed computing. It describes when we have a network of nodes, when one node sends a message to another node, how long does it take for that message to arrive? Okay, so there are a few well-established classic timing models. The simplest one is called synchrony. That basically says whenever someone sends a message to another person, there's always an upper bound, delta, for that message delay. And every message respects that delay, and everybody knows this upper bound delta. Okay. Then there's asynchrony that just says there's no such bound. Any message can take arbitrary amount of time, but eventually it will arrive. And then the third one is kind of a relaxation of asynchrony. It sits in between these two. It says the network model alternates between asynchrony and synchrony. So sometimes the network is asynchronous, but there will be sufficiently many periods of synchrony, and these periods are sufficiently long. Okay, so these three models are extremely well established. We have been doing research in consensus and many other problems under these models for decades. So why do we need new models? And okay, before going there, let me also clarify that the timing model describes not just the message delays. If we are more serious or rigorous about it, they should also describe clock skews, that whether my clock increases at the same speed as your clock, or the difference in that clock speed difference, whether it's bounded or unbounded. But for this talk, I will ignore clock skews. Let's just pretend that all of us have perfectly synchronized the clocks. Okay, so why do we need new model? The reason is that I believe synchrony is too strong. It's too optimistic as a model, but partial synchrony and asynchrony are too weak, too pessimistic. And it's not hard to see why synchrony is too strong, and I think most people in the field would agree with this statement, because if we design a protocol relying on synchrony, then we are really making this assumption that every single message respects the delay bound. If just a single message gets delayed a bit more than delta, then we lose all the provable guarantees. In some protocols, the protocol is just straight up broken. In other protocols, maybe there's not a direct break, but all the proofs we did no longer apply. And it's not hard in reality for an adversary to delay a message, or delay a few messages between two nodes. There are denial of service attacks, or an adversary may control a small part of the network, etc. Okay. But on the other hand, partial synchrony and asynchrony would be too pessimistic, because these models, they say the adversary controls the entire network. Every single message sent between any pair of nodes can be delayed arbitrarily by the adversary, of the adversary's choosing. It is unlikely to imagine there's an adversary that really is that powerful, that is able to manipulate all parts of the network at the same time. In particular, right, by now we know that the Bitcoin system and most of the deployed blockchains, they do not work in partial synchrony or asynchrony. Right? They would fail miserably in these super weak models. Right? But they have been running without interruption for more than a decade now, almost 2 decades now, right? And they are high-value targets. Right? If indeed there's an adversary who can control the entire network, we probably would have seen the attack by now. Okay, and this is more fundamental than this is actually a fundamental limitation, right? That the Bitcoin and most deployed blockchains, they do not tolerate asynchrony or partial synchrony because they just fundamentally cannot, right? Because most of these systems, they want to target a nice property called dynamic availability, right? That means not everybody is participating in the protocol all the time. Right? At any point, maybe there are only 20% of the participants that are participating in the protocol, and out of those, we have honest majority, right? And the majority of the nodes are actually not paying attention. If you want your protocol to be safe and live in such a dynamic available model, we have to forego partial synchrony and asynchrony. Right? It's pretty easy to show an impossibility, right? Because we can just partition the network into multiple small parts, right? And we as the adversary rely on asynchrony or partial synchrony to delay all the messages between these partitions, right? Then each partition, because it is unaware how many, what percentage of the network is actually participating, for all they know, maybe their partition is the only one who's participating, right? And so all of these partitions will take steps, right? Will make decisions independently, right? And that would lead to violation in consensus.
I wouldn't really say most deployed blockchains on this slide.
Yeah. Okay. Yeah. Thanks for that comment. I think nowadays the more blockchains move towards the more classic static availability setting. All right. And but if we think about the situation, there is actually a large gap between the three established models. On one hand, we have synchrony. Right? It's a strong assumption. Right? On the other hand, we have partial synchrony and asynchrony that are super weak, pessimistic models. Right? But there is a large gap in between. Right? And for the consensus problem, at least most of the important variants of it, right, there's also a separation between fault tolerance. Right? In synchrony, we usually require honest majority. Right? And in partial synchrony and asynchrony, the best we can hope for is to tolerate 1/3 of adversary. So now, given my claim, or hopefully I convinced you that synchrony is too strong and partial synchrony and asynchrony are too weak, right, then it's natural to ask whether we can find something in between. Right? And that is the topic of this talk. Right? Then we're going to introduce a new model called granular synchrony that basically covers that entire spectrum in between. The basic idea of granular synchrony is that we will not assume every link respects the bound or no link respects the bound. Right? We will model the graph, the network, as a graph consisting of a mixture of synchronous links, asynchronous links, and partially synchronous links. Right? And then depending on whether there are more, how many asynchronous links versus how many synchronous links are, right, the model is parameterized, and it can degenerate to one of the two extremes, or it can sit in between. Right? And in return, we will get a fault tolerance that also covers the full spectrum. Okay, so this allows us to have a trade-off between network connectivity and a tolerance against the adversary. Okay, so I will quickly clarify that this is a simplification. Right? In terms, when we compare models and their strength, there's more than one dimension. Right? So we cannot just put these models in a one-dimensional total order. Right? And sometimes some of the models are incomparable. Okay, so then next, I'll briefly mention some of the related or not so related models or works in the literature. Right? So there's some work on mobile sluggish faults or sleepy model. right? But these are orthogonal, because these are talking about type of node failures. Right? They're not talking about the links. All of these works, they still have to assume one of the three classic timing models, and they pick synchrony. And right, there are also works or models that consider links that are lossy, right? That the message may or may not arrive, may get lost, right? But this is also orthogonal, right? Because for the messages that do arrive, we still need a model, right? Whether they arrive on time or can take a while. And the most relevant, right, and to my knowledge, the only relevant work in this space is that there are line of works that study the minimum assumption required to circumvent FLP, and their methodology is to assume a mixture of asynchronous links and partially synchronous links, and that is indeed the same methodology that we take in this work. Okay? But as you can see, they do not consider any synchronous links, right? So their model is on my spectrum. It's also on that far right.
Who and when was that last paper?
So these are actually pretty old. I think around 2012, 13-ish. Right? And I don't remember the authors of all of those papers. Okay? And I will mention some of these works later in the talk. Okay, so next let me tell you about the granular synchrony model. Right? As I mentioned, we will model the network as a graph, right? And each link connects two parties in the graph, right? And each link may be synchronous, partially synchronous, or asynchronous. Right? Right now, our model assumes an undirected graph, right? Meaning that if I have a synchronous connection to you, then you have to have a synchronous connection to me. Right? So this is one limitation that I would like to get rid of, right? But so far we haven't been able to. And then as the model is sliding in between some of these extreme classic models, our fault tolerance, as mentioned, also slides in between this. Right? In the case of Byzantine faults, right, it's probably the case that's more relevant to blockchains, right? And it's somewhere in between 1/3 and 1/2. The main task that we have here is to identify the sufficient and necessary graph condition, right, under which consensus is solvable, right, for a given pair of N and F. And in this talk, for simplicity, I will focus on the deterministic case. Right? So the particles are deterministic, right, meaning that the parties or nodes will not toss coins.
Does a protocol know which links are which?
No, the protocol does not have to know which link is which, right? And when we prove the necessity of the condition, most of the time it applies to even protocols that are tailored towards a particular graph. We will study the agreement problem. Right? This is perhaps one of the most basic consensus variants. Right? In this problem, we have n parties. Right? Up to f of them can be faulty. And every party has an input. And so there are mainly two requirements, right, that such a solution to the agreement problem needs to satisfy. Right? The first one is called agreement, right, that correct the parties, right, non-faulty parties output the same value. And we need a second requirement that says if everybody has the same input x, then the output of everybody should be that input. Right? So this is the validity requirement is needed to rule out trivial solutions. Right? Otherwise, we can just there is a trivial protocol. Right? Everybody ignore the input. Let's just agree on 0. Okay, so let me start with the simplest case of granular synchrony. Right? We'll consider for now crash faults. Right? No malicious, no Byzantine faults yet, right? And we have no asynchronous links. So that means we have a mixture of synchronous links and partially synchronous links. Right? Just to remind everybody again, a synchronous link that says is one that says every message that goes on the link always arrives within some bounded time. Right? And partially synchronous link says that for a while, the messages on that link may take a very long time, but eventually we will get into a synchronous periods. Right? And during the synchronous periods, the messages arrive fast. Okay? And I should say that we're assuming that the synchronous periods of different links are synchronized, right? Meaning that there is a window of synchrony in which all partially synchronous links behave synchronously. In the crash fault case, we have these two classic results, right? That says if we're in synchrony, then agreement is always solvable, right? No matter how many nodes can crash. But if we're in a partially synchronous setting, then the best we can hope for is to tolerate minority crashes. So why is that? It's actually a fairly straightforward proof. If that's not the case, right, if f is exactly half of n, right, or n is twice of f, then we can divide these nodes into two groups, and then we can rely on partial synchrony to cut off the communication across the groups. Right? So then further, if half of the, if the left group, everybody receives input 0 there, and everyone in the right group has input 1, right? Then this will lead to an agreement violation, right? Because from the left group's perspective, it could be that all of these folks crashed, right? And everybody has input 0, right? So they would have to agree on 0, right? But for this group, right, it's the exact same situation, right? They do not hear from that other group due to partial synchrony, but from their perspective, it could have been that all of those crashed. Right? And so they will have to decide on one, and that's a violation of agreement. So now we'll move to granular synchrony. Right? In granular synchrony, we have a mixture of synchronous and partially synchronous edges, and our fault tolerance will also be in between those two extreme cases. And the condition we identified, right, that's sufficient and necessary to solve agreement in the crash no asynchronous link setting, right, it's this one. Right? It's a condition related to the graphs that says no matter which up to f nodes crash, there cannot be two disjoint groups of n minus f nodes that have no synchronous paths across them. Right? Pictorially, right, that says if the adversary, right, who is capable of crashing nodes, right, if there is a way for the adversary to pick a group to crash, right, and then after that there are two big isolated groups left who cannot talk synchronously with each other, then consensus is impossible. Otherwise, if the adversary cannot find a way to break the network in this fashion, then we can solve agreement. So for now, let me give you an example. Right? Since we're in the region where n is well, f is in between 1 and half, right? So let's suppose n is 1.6 f, right? So this is a dishonest majority, and if the adversary can corrupt certain nodes, I crash certain nodes, and then create two groups that are both pretty large, right? How large? Larger than n minus f. Then the adversary can successfully cause disagreement, right, among the parties. Right? Why? Because each of these parties is greater than n minus f, right? It's the same argument as before, right? From their perspective, it could have been that everybody else crashed, right? They are the only one left, so they need to make progress and make a decision, right? But then these two groups will make decisions independently, right? And that leads to a violation of agreement. So the necessity proof is basically the same as before, right? Okay, so then I'll directly go to Byzantine faults, right? Because I guess we or most people are not too interested in crash fault tolerant protocols, right? But I'll give you a Byzantine fault tolerant protocol in the granular synchrony model later. So now moving on to the Byzantine faults. In Byzantine faults, we also have two classic results, right? That says under synchrony, a Byzantine agreement can be solved even only if there is an honest majority, right? Or the Byzantine faults is strictly less than half. Right? In partial synchrony, agreement is solvable if and only if, right, the number of Byzantine faults is less than 1/3 of the total number of parties. Okay, so then we will consider granular synchrony, right, and we will show that agreement is solvable anywhere within that range. Oops, that's
That should
my
be n
bad.
over
That's a
3 and n
typo.
over
That's
2, right? That should be n over 3 and n over 2, right?
yeah, that's n over 3 and n over 2. Okay? And again, under a graph condition. Right? The condition is this one. It's also a little similar to the one for crash. That consensus is solvable if and only if, regardless of which F parties are Byzantine, among the remaining parties, right, there cannot be two disjoint groups, each of size n minus 2f, right, and they have no synchronous paths across them. Right? So again, let me give you an example. Right? If the adversary can corrupt certain nodes, certain F nodes, right, and then to disconnect two such large groups, right? For example, right, let's say n is 2.6 F, right, and then after corrupting F, two groups of 0.9 F and 0.7 F, right, that are disconnected, or cannot talk to each other synchronously, right? Both of these are larger than n minus 2F, which is 0.6, right? Right? So then there's no chance of solving agreement. Okay, so why is that? Right, this time it's because the middle group are malicious, right, or Byzantine, right? So they can play double agents, right? So they will behave towards the left group, right, as if they were the only one participating, right? And right, they will tell the left group, right, the right group never responded, right? Most likely they have crashed or they are malicious, right? And they will say the opposite to the right group, right? That they have never heard about, they have never heard from the left group. Okay, right? And again, because there are no synchronous path across the left group and the right group, right, then we can rely on partial synchrony to partition, right, those two honest groups. Right? So if you're familiar with the partial synchrony classic proof, right, this is the same thing. Right? Why do we need f less than n over 3 in the partial synchrony model? Right? It's because if that's not the case, then suppose n is strictly equal to 3f, then we can divide the groups into 3, right? Each of size f. And then the adversary corrupts the middle one, right? And the left one and the right one, like those two groups will make progress independently with the help of the F malicious parties in the middle. Okay, so once again, this condition is clearly necessary because of the split brain attack. And in a minute, I'll tell you how we can solve consensus in this model to prove this condition is sufficient. Okay, but before that, let me also draw your attention to the unifying power of the granular synchrony model. We can make the granular synchrony model degenerate to, right, both sides, right? But there is a footnote I put there. So let's look at the partially synchronous side, right? Suppose we do have n equals 3f plus 1, right? What happens then? There are 2f plus 1 honest in total, right? And this condition says consensus is solvable if we cannot find two disjoint groups of n minus 2f honest nodes. And that condition always holds, right? Because there just aren't that many honest nodes. Okay, right? So once we go to n equals 3f plus 1, agreement is always solvable, even if all of the edges are partially synchronous. On the other hand, if our n is 2f plus 1, right? So this is just barely honest majority. So then this condition says we cannot find two groups of one honest node, right? So every pair of honest nodes need to be connected by a synchronous path. Okay, but maybe you have realized, right, that doesn't quite degenerate to the synchrony model. Okay, right, because it just says that every two honest nodes need to be connected by a synchronous path, right, not a direct link between them. Right? So this actually leads me to realize, this is a misconception that even I and I believe my co-authors had, right? We thought granular synchrony degenerates to partial synchrony on one end and to standard synchrony to the other end, right? But that's actually not the case, right? It's only through discussion with Yuval that I realized, right, that's not the case, right? We actually have a somewhat new result here, right? That even, right, suppose we want to target n equals 2f plus 1, right? The strict honest majority, does that require fully synchronous work, right, for consensus to be solvable? Most of the existing protocols do require that, but turns out that's not necessary. Right? Right. Let's consider a graph like this, right, where we have f nodes, right, and then the remaining f plus 1 nodes form a line. Right? But all of them, right, there's a like dense pairwise connection across the two groups. Right. On this graph, agreement is solvable, right? Even though we do not have full synchrony here. Right? In particular, we have no synchronous edges in the bottom graph other than the line. Okay? I think this is a somewhat interesting observation. Right? That if you are super familiar with literature, you can probably piece together some hints from some prior works, right, to realize right, this fact. Right? But at least I personally didn't know this before doing this work.
So there's also a partially synchronous analog of this observation, or not?
No. On the other end, it does properly degenerate to partial synchrony.
Why are they different?
Yeah, perhaps you can argue that standard synchrony maybe should just be defined this way, right? That the extra, right, that it doesn't require pairwise synchronous edges. Right? This many synchronous edges is sufficient. That having even more synchronous edges beyond this minimum condition may make it more convenient to design protocols, may make your protocols more efficient. Right, but in terms of feasibility, right, it's not the fundamental condition.
So to what extent, I mean, can I just, if you tell me that there's a like synchronous spanning tree, can I just think of that as like synchronous all-to-all, except with delta replaced by n times delta, something like that? Just by flooding, basically?
Yes, I think that's a simple transformation.
Okay.
Yes.
So that would say this distinction, so that's a way of formalizing what you just said, that the distinction is really just about kind of efficiency considerations, not
Yes.
about possibility considerations.
Yes.
Okay.
Yeah, that's a good point. Yeah. That you can add a wrapper on top of this network to make it a fully synchronous network with a worse delay bound. Yeah.
And then different questions. So, like these conditions, like if you gave me a graph, it would be hard to check if these conditions were
Yes,
true. Yes,
I will talk about that in
It's like a balance. It's like a minimum balance cut type problem, right? To even check the condition, right?
Yeah. Let me talk about that in a.
Okay.
Let me answer that in a bit.
Okay.
Okay. So next, I'd like to tell you how to build a consensus protocol in the granular synchrony model. Right. I will not give you all the details, right? But I think I will be able to convey the crux of the matter here. All right. So let me start with a classic partially synchronous BFT protocol, right? Like PBFT, Tendermint, right? They all roughly work like this. It's organized in a sequence of views. Right? Each view has a unique leader. Right? These protocols may do round-robin leaders or randomized leaders. And within the view, right, let's say this is a view number k, right, the leader will send a proposal. Okay? It will pick a value and send it to everybody. And then other nodes will vote in 2 rounds. Right? So they will first do a 1 round of voting. Right? And if they collect n minus f first round of votes, then they will lock on that value. Right? We'll talk about what lock means very soon. And then they will also send a round 2 vote. Okay? Then upon receiving n minus f round 2 votes, they will decide on that value. Okay, so then there is after that there is a non-trivial procedure called view change. We go to a next leader, but this is the basic idea. Right, so how many of you are familiar with this type of protocols? Okay, yeah, most people here. All right, so why is this a secure protocol? Right, we mostly need to worry about safety within a view and safety across views. Right, within a view, this is sufficient, right, because in order for one node to decide a value, there are n minus f who need to vote for that value. Right? And if you want a conflicting value to be decided, then there are n minus f who need to vote for that conflicting value. Right? So then there's a standard quorum intersection arguments. Right? If you have n minus f voting for x, n minus f voting for x prime, right, then the intersection between these two groups is their sum minus n, which is n minus 2f. Right? And in the classic partially synchronous protocols, n is at least 3f plus 1. Right? So that intersection is at least f plus 1, which means there is one honest in the intersection, right? Which means that honest node double voted, right? And which would not happen, right? An honest node would not double vote, right? So we cannot have two large quorums voting for conflicting values. Now, safety across views is slightly trickier, right? That if one node decides on a value, right, and this is where we need this notion of lock. Right? N minus f must have voted for it and must have locked on it. Right? And then in a new view, a new leader, when the new leader wants to propose a value, right, it needs to respect the locks. Right? It needs to go and ask people, what values are you currently locked on? Right? It needs to collect these locks and show these locks to justify its proposal. Right? If somebody is, and the leader is required to repropose the highest lock, right, if there is any lock. This is also a quorum intersection argument, right? So there are n minus f who locked on a decided value, right, and the new leader must show n minus f locks, right? So that intersection is again f plus 1, which contains at least one honest node, and so that honest node is guaranteed to inform the new leader of the potentially decided value, right? So the new leader will have to repropose it. Okay, so this is the basic idea behind PBFT, Tendermint, hot stuff, pretty much all the partially synchronous protocols. Okay, right, so now we will try to adapt this protocol into the granular synchrony model. Right? But the main difficulty is that now we're in a regime where n is at most 3f, right? Smaller than 3f plus 1. Right? So then our quorum intersection argument breaks down. The intersection is at most f. It could be that all of them are Byzantine, right? And the Byzantine can indeed double vote. The Byzantine can indeed pretend to lock something and then later say they never locked. Right? So we need to rely on the granular synchrony graph condition to fix this problem. Let's take another look at this our train of thoughts. Right? If one person decides, then n minus f have voted for it. Then n minus 2f honest nodes are among the people who voted. Right? So n minus 2f is a special value for our granular synchrony model, right? Because our model says, regardless of which nodes are Byzantine, there cannot be two disjoint groups of n minus 2f. Right? What that means is that if one group is at least n minus 2f, then the other group is smaller than n minus 2f. Right? So they're f corrupted, right? And this right group is less than n minus 2f. Right? If we add them up, that's less than n minus f. Right? What that means is that this left group actually has to be larger, right? So this doesn't add up to everybody yet, right? So there's additional nodes who have to be connected to the left group, right? And these connected component in total is at least f plus 1, right? Because these two add up to less than n minus f. So what that means for us is that now when we, let's just, as an example, I'll just do safety across views. Within a view, it's about the same. When one node decides n minus f lock, n minus 2f honest lock, they are connected to f plus 1 honest nodes due to the granular synchrony condition. They are connected via synchronous paths. So if we just give them a little time, they will be able to transfer their lock to this larger group. This n minus 2f who initially locked, they will send their locks to other people, and in a little bit time, these locks will propagate to a bigger group of size f plus 1. And then a new leader comes in. The new leader needs to collect the n minus f locks, and now we again have an intersection. This n minus f and that f plus 1, they intersect at least one honest node. So that honest node will transfer the lock to the new leader, forces the new leader to repropose the potentially decided value, and we get back safety across views.
That's right. So the f plus 1, that comprises both the n minus 2f people who honest voters plus the people they can reach by synchronous paths.
Yes.
Okay. So that f plus 1 refers to those two white circles combined.
This combined is f plus 1. Yes. Okay. So yeah. So this is the basic intuition. We pretty much, whenever we need a quorum intersection argument, we will invoke this argument to essentially upgrade our n minus 2f quorum to a f plus 1 quorum. And that f plus 1 quorum will intersect with the other n minus f quorum.
So you have like 2 new rounds per view or something like that? Or?
Yes, we need, with the protocol, in what I'm presenting, the protocol is not very efficient. We actually need a lot more rounds, because because this may not be a direct connection. This is just a path, maybe a long path. So we actually may need to make that an n rounds waiting time. Okay, yeah. So now I'll get back to Tim's 2 questions. First, the algorithm is graph agnostic. It never examines which link is synchronous versus partially synchronous. But the conditions are necessary even if you want to tailor an algorithm for a particular graph. The other question from Tim is a great one. Is that how do we know that granular synchrony condition holds? So I also struggled quite a bit when working on this. That it seems unrealistic to go out to the field and measure every link to label each edge whether it's a synchronous and partially synchronous, and then check the graph condition. But eventually, I convinced myself this is not a problem, because we just don't have to check. And I compare this to what we currently do. We currently assume that the adversary cannot corrupt F nodes. Why do we believe that? We never went to these nodes to investigate their security practices, whether they whether they regularly update their software, whether they like to accept bribes, whether they have financial ties with different other nodes. We just assumed that no more than F can be corrupted. If no more than F is corrupted, our protocol works. If the adversary manages to corrupt F plus 1, then our protocol fails. And there's nothing we could have done. If indeed the adversary corrupts more than F, where F is the 1/2 or 1/3, whatever the limit is. So I would argue that the situation here is the same. I just assume that the attacker cannot corrupt the network so badly to create these large groups. If it cannot do that, then our protocol works. If it manages to do that, then our protocol fails. So I think the situation is not too different from what we currently do.
I'd say I only half agree with you in the sense that One question is just what are you in a position to monitor? So this is the point you're making, right? So maybe you can't monitor if a node is faulty, and you can't monitor if a link is synchronous or not. Right, but the point is, it's like if you, but then like suppose you could monitor, right? So if you could monitor who was faulty or not, it would be trivial to check whether the bound of f held. Suppose I just gave you, suppose I just told you the synchronous links and the non-synchronous links. Then there's the computational problem of given that information, does the bound hold? And the point is, like, if the graph is big, that is also going to be quite non-trivial to check.
That may even be an NP-complete problem.
It's definitely an NP-complete problem, So, I mean, I think there's a second issue here that's not there with just the fault bound, so.
Yeah, I would agree with you if you take that view, right? I think I just don't feel whether we even go there, right? Because I don't think any protocol did any checking of who's malicious, who's not malicious, right? Because even then,
well, like crash faults, you could certainly do this, for example, right?
Yeah.
I mean, like the idea of like monitoring is not crazy, right? And like it's going to be only partially successful, but.
Okay, yeah.
It's NP complete, but you can approximate it, which means that you could probably still get some guarantees if someone were to give you like all of the information about these guys are synchronous, these guys are asynchronous, you'd still be able to get something better than just knowing how many people are faulty.
Have you looked into the approximation factor?
I think the approximation factor is like log n for balanced vertex cut, which
with
would render you
a non-trivial
resilient to
leading constant. Too.
Yeah, exactly.
Yeah, I think if we really have to check, perhaps we will have better luck with like heuristics, like SAT solvers. And stuff like that,
I mean, it's possible that the mathematical program relaxations would do well in practice, and you'd do well. I'm not sure, but I'm just saying, like, there is this. Like, so, like, what would be like one thing? I don't know if this is true, but like, imagine you could have a protocol that worked even if a certain like semi-definite programming relaxation of the network was sufficiently, large or something like that, right? Then you'd have a efficiently checkable condition that would be sufficient for consensus. So that would be like a stronger result, for example.
A stronger, yeah.
Yeah.
So with that, I think there's an alternative interpretation of the granular synchrony model. Right? That is, a protocol designer picks a pair of n and f, right, and wants to deploy a protocol with these two parameters. Right? And the adversary can corrupt nodes, and it can corrupt links. Right? Corrupt links meaning slow down links to make it partially synchronous or asynchronous. Right? But the adversary is assumed to not be able to create these two large disconnected groups. Okay? Hope it's not too hard to see that these are essentially saying the same thing. So lastly, very quickly, I just give you some food for thought, right, for the summer. Right? There's future directions that I'm interested in. Okay, this part is perhaps a little interesting, so let me spend a little more time on it. Right? And so far, we have not added asynchronous links. Right? So now let me add back asynchronous links. Now we have three types of links: synchronous, partially synchronous, and and asynchronous. Right? And in this case, agreement for crash faults is solvable deterministically if and only if, first, the previous no split brain condition holds, and another complicated graph condition that I won't go into the details. But the interesting thing is, right, what I want to highlight here is that now if we consider f is strictly less than half, right, so we're not trying to go to the intermediate corruption, then we know this first condition, it becomes vacuous, right? It always holds, right? And then agreement is solvable deterministically if and only if this other condition holds, right? So this could be interesting and significant to some people, if you care about the fundamental results of consensus, right? Because this is the minimum condition to circumvent FLP. Right? FLP says if all links are asynchronous, then consensus is not solvable deterministically. Right? What this result is saying is that if there are sufficient partially synchronous links to satisfy this graph condition, then consensus can be solved deterministically. Right? And in fact, this disproves a prior conjectured minimum condition, which is, I said something else. It's another graph condition that's strictly stronger than the one we found.
So this is a new result.
This is a new result.
Okay.
Okay, and then there's a counterpart in the Byzantine case, right? But in the Byzantine case, like, we were only able to prove a negative result for graph agnostic algorithms. For graph tailored algorithms, it is still open what the necessary condition is, right? So there's some open problems here. Okay, so to summarize, a granular synchrony model has some nice properties. It's weaker than synchrony, allows some messages to take more than delta. It tolerates more faults than partial synchrony and asynchrony. Right? It naturally unifies the two models on the extremes. Right? And we have identified the necessary and sufficient condition for solving consensus there. But there's still quite a few open problems here. Right? The first one is that we can study other problems in this model. Right? Consensus is not the only problem that involves parties talking to each other, sending messages to each other. Right? There are a bunch of problems in cryptography as well. Or even in consensus, there's still like reliable broadcast, right? And in crypto, the verifiable secret sharing, multi-party computation, etc., right, can be revisited in the new model. Secondly, the protocols I presented are fairly inefficient because it requires a lot of forwarding, right? And Yuval is making some exciting progress, right, that shows we can actually get pretty efficient protocols that asymptotically are as efficient as the ones in pure synchrony and pure partial synchrony. Okay, right now I'm assuming undirected graphs, right? So it's interesting to see what happens, right, what changes in the directed graph, and you can combine it with other models, right? But bigger open problem, right, is that may have under-delivered a bit. Hopefully you didn't know this so far, right? That when I set out to discover, to define a new timing model, my primary motivation is to try to capture dynamic availability. So right now, Bitcoin and all of the dynamic available protocols have to be analyzed in the synchrony model, not because it fundamentally requires synchrony, it's just that we don't have any other model that we can use to analyze them, right? So I was hoping that we would find some intermediate model between synchrony and asynchrony that still supports dynamic availability, right? But granular synchrony, at least the condition we identified was not that, right? Because it's pretty much tied to full availability. Right? It says as long as there are no too large components, consensus should be solvable, but in a dynamic availability problem, even small isolated group, I will make a conflicting decision. Right? So I would say this problem is still open. Right? I'm still searching for the right model for large-scale distributed consensus that hopefully supports dynamic availability.
So if you relax the condition that either like all the links are synchronous or in partial synchrony at the same time, do you have like thoughts on what happens?
If all the links are...
Like if you allow the timings of when things are synchronous to be interleaved somehow?
If the partially synchronous links are not synchronous at the same time,
Yeah.
no, we haven't thought about it.
Okay. I guess maybe relatedly, if you have something like an adversary that's allowed to like have some fraction of the links they switch from time to time, so like either things are synchronized or they're not, but like an adversary chooses which ones to corrupt. Is that connected or known at all?
Wait, can you say that part again?
So like
You can
so I guess like
corrupt-
it is in between things being arbitrarily interleaved or like perfectly synchronized. Say an adversary is like allowed to have some fraction be not synchronized and some fraction be like interleaved.
Are you mainly interested in that the adversary moves around?
Yeah. So like
okay,
they
we
can't corrupt all the
haven't-
links at the same time, but the network maybe
Right,
for some
we
of the
haven't
links,
considered any notion of an uncorrupted link or uncorrupted node.
That usually makes stuff very hard, very quick, right?
Yes, I think it might be slightly easier for link. Right? For node, yes, there's some keys involved. Once you corrupt a node, it learns the key, and it's unclear how to uncorrupt it. But for a link, at least the notion of uncorrupt is clear. Right? But I think the challenge there is that you cannot let the adversary jump back and forth too quickly. Right? And so there needs to be some cool-off in the model.
So on this last slide, so did you say that the condition, you do know that the condition that you identified for strict majority with full availability is not sufficient for dynamic availability? Did you
It
say
was
that?
not sufficient because it's in particular it allows small isolated groups, right? The only thing it doesn't allow is two big isolated groups, right? But with dynamic availability, even a small isolated group will cause trouble.
And so do you have like a conjectured necessary condition or?
Yeah, not.
Okay.
Yeah, nothing comes to mind.
I like your comment, Tim, about the coming up with an STP or an LP that will be maybe like a relaxation of that condition to a more continuous model, and then prove that that's tight. I don't know how you would model a link though in that case. Like I don't know, maybe all links are synchronous, but just like with very large bounds, or something. I don't know.
Thought Tim's point was mainly that find a maybe slightly stronger condition that's easy to check. Like that.
Yeah, that's one version of it, definitely. Yeah. Basically, insist on easy to check and get whatever you can get. Was sort of the thing what I was thinking. Yeah. And if you can get everything you have now and it's easy to check, then all the better, right? But maybe you need some trade-off. So.
Sorry, coming back to Pranav's question about the adversary moving, if the protocol is network agnostic, I shouldn't be making decisions based on whether this link is synchronous or not, right?
We are not, right?
So what goes wrong when the adversary moves around on the links?
Let's see. Because these protocols, they have a unit usually called a view. You want to argue that a view succeeds, right? So if you let the adversary corrupt part of the network in the beginning of the view, right, and then move to a different segment of the different part of the network in the middle of the view, right? So then it can.
I see.
Right. Yeah. So that's why I feel intuitively, if you built in some cooldown period, right? When you uncorrupt the edge, you cannot immediately corrupt another edge. Things might work.
So there's no explicit attack as such. It's just that we don't have the proofs techniques, or?
I can probably come up with a explicit attack if there's no such cooldown. Right, or, right, okay, a very easy attack is that I always corrupt all the edges of the leader, right? That actually doesn't violate the condition.
All right. Let's thank Ling again.